This is our last video of the week, and in this video we're going to talk about effect modification. We're going to explain what we mean by this and also how to identify effect modification. We're going to suggest ways in which you can deal with effect modification if it's present in your data, and we'll give some examples of effect modifiers as well as of confounders, because remember, they're variables. A third variable could be either. Effect modification occurs if the effect of the exposure is inherently different for different groups. For example, males and females have different physiology, different hormones, and therefore the effect of a particular drug may differ in these two groups. It has nothing to do with unbalanced selection or anything like that. It's because basically there's a different response in the two groups of the effect modifier. It also involves a third variable, which is not the exposure or the outcome, and it's a natural phenomenon. It hasn't been caused by any design issue. With effect modification, therefore, we end up with different odds ratios for each stratum. An example might be measles vaccination in children. If the vaccination is done in children who are older than 9 months of age, we get 95% protection. But if we do the vaccination in children who are younger than 9 months of age, we only get 75% protection. So this corresponds to odds ratios of 0.05 and 0.25. So you see the odds ratios are different depending on the age group. How do we identify a suspected effect modifier? Well, we start off the same way we would with looking for confounding. We would calculate the odds ratio for the entire combined sample. Let's say it came to 2.3, and then we would stratify by the two levels of the effect modifier, and we would work out the odds ratios for each stratum. Now, in confounding, remember, both odds ratios got less than the combined one, or else they got greater than the combined one. And we had a rule that said if that difference was more than 10% from the combined value, then confounding was probably present. Now, with effect modification, they don't move to the same side. So one of the strata, the odds ratio will become less, and the other stratum, the odds ratio will become more than the 2.3. So we had 2.3 for the combined group, and then when we stratified, we got 1.8, which was less, and 3.7, which was greater. So the odds ratios diverge when we stratify. And if this happens to a convincing extent, then we suspect that there's probably effect modification present, and we can go on and do a statistical test for that, unlike with confounding. So for effect modification, we don't have a 10% rule of thumb. Remember, for confounding, we said if it's 10% difference or greater, then there's probably confounding present. This doesn't apply for effect modification because we now have a statistical test that we can perform. So as long as it's by a convincing or appreciable extent, then we can develop or generate an interaction term and between the effect modifier and the exposure, and we can include that in our regression modeling or regression analysis, and if that term is significant, then we've shown that effect modification probably exists. And in that case, we need to produce two odds ratios, one for each stratum of the effect modifier. If we show that a variable is an effect modifier, then it can also be a confounder of the same relationship. However, we don't have to worry about this because due to the fact that it's an effect modifier, we're going to stratify anyway. So if there is any co-confounding also present, we'll have dealt with this through stratification. So we don't have to worry about the fact that there may both be present at the same time. We start by looking for effect modification. If it's present, we stratify. And if there happens to be confounding, that's been dealt with. So yes, as with confounding, we have solutions. All is not lost if there's effect modification present. On the contrary, you could study each effect modifier stratum separately. If you've combined them in one study, you could produce a set of stratified results with separate measures for each effect modifier stratum. And we can identify this and see if it's statistically significant by doing regression analysis, and you're going to be exposed to that in the next module. Now, in fact, age might be an effect modifier for a particular exposure disease relationship, and it might be a confounder for a different disease exposure relationship. So these variables, these third variables, in some contexts may behave as confounders, and in some they may behave as effect modifiers. And some common ones that are often used: age, sex, smoking, alcohol use, socioeconomic status, and so on. These are pretty generic, but when you have a particular situation, you'll also have very specific possible effect modifiers and confounders present. In conclusion, if an effect modifier is present, then stratification will produce a divergence of the odds ratios, either side of the crude. And secondly, if you have effect modification present, then you must present two odds ratios or relative risks, one for each level or stratum of the effect modifier. Of course, if your effect modifier has got 3 or 4 levels, you'll have to produce 3 or 4 odds ratios because they may all be different.